stop class a little bit early today and then go on a little field trip towards the end of class. Just because I want to show you, and then blah, 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 and then we'll stop at my office, so I'll be there, haha. Alright, so that's what we'll do at the end of class. Are there any questions on anything we did last time before I get into? Yes?
Can I ask a question before coming in?
Okay, let's see what it is.
The problem, what was the
Last
I think it's number 46.
46.
46. In 12.1.
Ooh, yeah, I like that one.
Is there a three-dimensional unit circle? Or I haven't been told about.
Well, this one is less... How do I say this? So, the problem with the form... So here's the problem. Number 46 gives you... And very quickly, this is the equation of what, for example? What is this the equation of? Circle. Of radius centered at the... Sweet, all right. So this would be the equation of what? Sphere, radius 4, centered at the origin. Sweet. So the problem with the equation they gave you, the very first one, the problem, so it might be good to know. It's like, where's this thing centered? What's its radius? Then you can actually figure out its volume directly, just using the volume of the sphere. Now the problem really says find the volume that's contained in both of these, right? And the other one they give you is a nice easy one, of course. Where'd you go? There you go. So, what do you think? Like, for example, if I gave you two circles and it said find the area that's contained in those two circles, that would be a decently difficult problem, but
Switch it to polar. Okay.
possibly, sure, right? But did any of the examples? Did you find an example that was kind of related to this? Do they have an example in the section that was related to this? So something that we haven't even gone into directly yet, but you've certainly seen some of it is 3 dimensions. So you're all cool with this being the equation of a sphere. The z-axis exists, and one reason why I like to do a little bit of section 12.2 first is to really identify why we use the z-axis that we do, and how it relates to the x and y axis vector-wise. All right, so I like to talk about vectors a little bit first. But I mean, what'd you try to do? I mean, it's a little difficult to graph in 3D. We will still try to graph some in 3D. I want to show you... Oh, that's what I meant to do. Shoot. I got to get Wolfram Alpha's player working on this. It's a really good idea, especially for this class, to pay for Wolfram Alpha full access. Because 3D is, back in the day, my instructor drew worse than me, and he's trying to draw 3D images, and we're like, oh my God, please, someday technology will catch up. But now you go Wolfram Alpha, graph the 3D plot, rotate it. My God, if you can't rotate it, you really can't see what's going on. Okay, with all that said, that's why I drew the 2D analog to kind of, you could start there and think about how you would attack that. So this is a sphere at the origin of radius 2, and this is sort of how you do 3D stuff. You have your x-axis, your y-axis, your z-axis. Bam, bam, bam. Right, so a little sphere of radius 2. You just go 2 out in all directions. So that's easy enough so far. And then how do you make that a sphere? Well, very often what we'll do is we'll draw like slices of it. So there's a slice there. Here's a slice on the this way, right? And it's not the best, but it kind of, you can start to see how it's forming a sphere, sort of, right? So it's sort of like having this and then having that, and that looks a little more 3D, especially considering I can't draw worth shit. That looks more 3D than just, that. So that's this guy, and then this guy is another sphere sitting at a different center. Who knows what the radius is until I do something. All right, so that's the idea. And then I want to find the volume contained in both. Right? I like it. Cool. So you could try to draw it a bit to see what's going on. What have you tried so far?
Well, like Micah said, if you integrate based on these 2 points where an intersection from one side and the other side, but there's no three-dimensional intersection. You have an infinite amount of those cuts. It's not.
I see. Okay.
It's not
So first off, how do you find the points of intersection?
7 equal. 7 equal.
All right. So how do you do that? How do you mean set what equal?
The 2 equations. Right.
Okay. But where would you go from there? I mean, what do you really mean when you say that? I mean, so how would you do that?
So you would subtract 4 and then you make it 0.
Okay, sure, you could do that, or you could just say this equals 4, so then that's 4, right? So really, I was looking more for you to say substitute.
Okay.
But you'll get the same place either way. But to me, that's 4, so anywhere I see that, I can write it as 4. But I mean, do you see how that doesn't really give you all the points of intersection, right?
Yeah.
Right.
Okay, good. So I mean, that's the first problem to overcome, right? All right, cool. All right. The rest of you, I don't know if you've even looked at this yet. So that's why I'm trying to give you little things to try. I want more of you to try this out before you go too far with this problem. This one I think is the most challenging one in this section. But I thought for sure, did they not give you?
No, there wasn't.
Oh, good. Okay. So it's even more challenging than I thought it would be. I like it.
Are you talking about like factoring out the whole equation?
So I mean, if you do what we're saying, so we know that this is true. We know that's 4. So I could put a 4 here, right? So I get 4. So 4 to 5 is 9. So I get 4x minus 2y plus 4z equals negative 9. All right, let me stop there for a second. Is that cool? 4 and 5, 9, bring it over. I mean, and then that, we haven't even talked too much yet about what that means and what that represents.
That'll just be a plane, right?
That's a plane. And which makes sense if you think about it, in a way.
It'll really be a circle on the plane.
Exactly. It'll be a circle on that plane. But then how do you go from there? So maybe this is not the best approach to take. I got you. I'm with you. All right, I don't want to give too much away. How many of you guys have not tried this problem out yet? Be honest. All right, good. All right. So I want everybody to try this problem out first. I mean, if you have an idea, try to attack it. If you want to, you can come by and I'll give you some more hints. But I don't want to say too much before people have all tried this out. So, did every other problem go okay with people that did that first? Yes.
I would.
All right.
So would you have to find the center first and then do the volume?
That's one thing I was saying. It might help to find out more information about this sphere. Right?
Well, couldn't you complete the square
Exactly.
to put it in a more standard?
That's not a bad first step, and then see if that information helps somehow. Right? Yes?
To know the answer to this problem, I don't want to say it, but the biggest problem that I noticed reading through the textbook about regarding this is it's giving you a problem and then it's telling you to solve it. And in the examples in that book, in that section, they don't like properly teach you the mindset of like, okay, if you have 2 equations, you need to extrapolate all the information out of it and then use that information to basically as a tool to
Yeah.
find your answer.
Well, where you guys are now in this Calc 3 class is you're sitting on a huge history of tool acquisition, right? You guys have gone through a lot of courses, a lot of math courses. You have a ton of tools at your disposal, possibly integrals, definitely completing the square kind of stuff, all these different tools to try to throw at a problem. That's why I love this problem, because exactly what you said. If this is the only problem you have trouble with in this section, then you're doing fine. Because this problem, I remember, I'm like, oh yeah, this is cool, let me see what they do with this. Sometimes that happens, right? So I just want to give more of you guys, a lot of you guys haven't even looked at this problem yet, and I'm giving you a little bit of an idea of what to start with. If you haven't tried to get more information out from the sphere, do that next. See if that helps you with something, right? Does that, you guys see at least where to start if you haven't tried this problem out yet? Okay. Okay, well, we haven't even talked about stuff in 12.1 at all yet, but that, I mean, a lot of the 12.1 stuff you've picked up a little bit along the way. So, cool. I like it. All right. Anything else? Yes?
They have the same pages.
Say again?
They have the same pages.
All right. I didn't want to say anything until...
Okay.
Yeah. So if you complete the square, what do you get? Yeah, you'll get...
X plus 2 squared,
X plus
y
2
minus
squared.
1 squared, c plus
4, 5, 4, 5, 4, 18. Do they have the same, really? No. No, they don't. Yeah, it'd be 4, 4, 1, 9, 9, 4. Yes, they do. Yes, they do. Okay. So maybe that'll help out. I mean, it's when you see a problem and the radius comes out nice, that they made it happen that way. So maybe that'll help out. You know what I'm saying? If I just made numbers up and shit, I mean, that radius is going to be gross. That's all there is to it. But they forced this one to come out nice, right? That 5 was selected. So maybe that has something to do with it. Oh, you guys look so excited. Again, if you haven't tried any of the homework yet, that is the hardest problem in that section. So don't gauge your ability to do it on that one problem, right? That is not an easy problem. But you're starting to see the ways to attack that. I don't want to give you too much, really. I want you to try to attack this with whatever you know. Just attack it. And nowadays you have the stupid internet. My God. I'm sure out there somewhere there's an answer to this. You just, there it is. But don't do that. Don't try to go straight to that. Try to attack it with what you know. Right? Don't attack it with fire. Attack it with what you know. Fire's not necessary yet. All right. Okay. So anything from that handout we did, is there any lingering questions or any questions about what I expect you to know going in? Have you all gone to the website and looked at that trig sheet, for example? So you kind of know what I expect you to know? Do you know what the trig sheet I'm talking about? How are you guys doing? You all right? Is your first week going okay so far?
Yeah.
You look shell-shocked. I'm sorry. Some of you guys taking too much math? Anybody taking physics also at the same time? Anybody? Sweet, look at you guys. You electromagnetism? Anybody in there? Sweet, yeah, kick ass. I'm sorry. It's one of my favorites, man. All right. So there's no other little questions. We're going to get back into start looking at this stuff. We did talk a little bit about the notation I'm going to use. So this would represent a vector. And a vector lives independent of coordinate system, possibly. We'll put a coordinate system on it so that we can give it names, we can better define it. But it could just sit there living on its own. It doesn't need a coordinate system. And we talked about, what would this be? Tell me something about it.
It kind of needs the coordinate system to have a direction, doesn't it?
Well, the reason I say it lives independent is because you can actually align the coordinate system any way you want to, and actually in all 3 dimensions if you're in 80 dimensions if you wanted to. Let's not go there. Let's stick with the ones we live in, the 3 dimensions. So, I mean, I could orient it so that it is exactly like I expect you, or I could make it so that this lies entirely along the x-axis. So, I take your point that before I give it a coordinate system, I can't really define the direction. But that's what I mean. Does that vector exist? Yeah, there it is. I can point at it. Look at it. What direction is it pointed in? Well, I don't know, Jeff. I mean, do you want to call that the positive direction, or do I want to call that the positive direction? Do I want to call, That's what I mean. And anybody in physics, that you can define which way is negative, which way is positive. That's just the direction, right? Okay, I'm with you. So that's why I need to put a coordinate system so then I can better define things about it. I love it. A scale would tell me how long it is based on what coordinate system, how I want to do the units on the coordinate system, right? This would be, though, how related to this?
Twice the magnitude.
Good. Can anybody tell me one more fact? Say again.
Positive direction.
It's in the same direction as this. Whatever direction this is, whatever coordinate system I plan to use, or however I want to orient it, this is going to point in the same direction as that. I like it. Cool. So, in order to do more math with vectors, we do have to introduce a coordinate system. But before we get there, say a few things here. So, let's see. If I have a vector u, which direction do I want to go? Sure, that'll work. Oh, let me do this. Let's give ourselves a coordinate system. Let's do it the way we're used to. Okay, cool. And so if I have a vector u, I want to give this thing a name besides just the u vector. I need something, a name that's more specific about what that vector does. So there's a couple of options, and the most immediate option is what point does that vector point to? Right? And the reason that kind of makes sense is, so let me give myself a scale here. Sure, Jeff. Good job. So what would I call this vector? That was another name for this vector besides u. It's related to the point that it points to. I don't want to give it, it's not a point though. I don't want to use parentheses. So what we actually end up using are these things that look like inequality symbols. So it points to the point 3, 2, so I call this vector 3, 2. Beautiful. I always have trouble figuring out, there's a lot of different orders I can do stuff in. So I've got to kind of fill it out as I go. The math involved in section 12.1 and 12.2, besides that one problem, is not taxing at all. How are we doing so far? That should be old news for some of us. Especially if you've taken physics, this is like really old news. So if I had another vector sitting here, oh, my scale's almost the same, good. Sitting here like this. Weehaw! So what vector is that? I'm going to call this vector v, but it also has a name what? 1, negative 3. I like it. Now, vectors can represent anything that has direction and magnitude. You with me? So very often I kind of default to think of them as forces because it's a really nice image. I've got somebody pushing a box this way and somebody else pushing a box that way. Right? So if I was like, help me move this table, and I'm pushing this way, and then you come in and push that way, I'm like, well, okay. Which direction are we going to go? I'm going to steer the table. So if you push this and I push this, we're going to go obviously in that direction. So the idea of adding vectors makes a lot more sense when you realize it's just adding forces to get the resultant force on something. So these represent two people pushing with some kind of force on some object. Now, right now, they're drawn in standard location, right? If I draw it starting at the origin, then it's the standard location for a vector. It's where I have to draw it so I can see its name. So if I pick this vector up and I moved it somewhere else, pick it up and I move it over here, it is still this. That is its name. That is the vector. So the name of the vector in this kind of coordinate form is based on where it would point to if you put the tail of it at the origin. Are you guys still kind of with me? Let me stop there and make sure you guys... All right. Yes, sir.
Is there a way in which you specify where it is in a coordinate system in certain cases where you would need to?
Totally. When we try to... You think that lines are simple because you've looked at them in 2 dimensions. Now, anything you've ever drawn in your life has existed in more dimensions than you realized. And obviously, if I go into higher and higher dimensions, then the formulas used to describe those things will get more and more complicated. All I should have just said, I forgot your question, but yeah, I'm going to have to identify where this starts. So if my line was this line, if that's my line, doesn't V represent the direction it goes somehow?
Yeah.
Isn't V then something related to the slope of that line?
Sure.
Let me stop there for you guys to see what I'm saying. You guys cool with that? All right, obviously these two are in different directions, but if that's a line and I'm trying to come up with an equation for that line, this is in our future, I can use this as the direction, and what's the other thing I need? I need a slope and a
Intercept.
point, right? I like it, all right? So, for example, this is getting a little ahead of us, but I love it because of the question. If I had a line like this, I'm trying to draw a parallel, you with me? It's defined by two things. It's defined by this vector and this vector as a direction. So you can kind of start to imagine how I could piece together that equation of the line. So to be honest, so what was you again? What's the name of you? 3-2. Come the thingamajig. And then I would add pieces of this vector, certain multiples of that vector. It's sort of like that's the slope, and then I can multiply by the variable. Just like I'd say 5 plus 2x. This is constant plus t times direction.
What's the T?
T is just like parametric stuff. So it's my general all-purpose variable. So do you see how that's a lot like mx? Well, let me do it this way. Mx plus b, right? Slope variable plus starting point. Interesting. I know, and I went a little too far ahead, but don't worry if you don't quite get that. That's perfect. We're not really there yet, but it was a good question that was asked. All right. So there are going to be instances when we want to identify this line, and it is over here. So I know it's based on this, but it's got to have its own. I need to pick these points up, and that's how I kind of do it. I can move that over, but still use the direction that this defines to help me. Yes?
So to summarize, to describe that vector that's away from the origin,
This here.
you start with, you add like the directional vector, in this case b, you add the vector that moves it.
So let me do, yeah, exactly. Let me back up a second. I haven't actually talked about adding vectors yet, so it was a little bit of a step for me, but I want to make sure this makes sense. If I want to add these two vectors, let me just take this away again. I'll bring it back in a second, because this, I personally, I love this idea. It's just so beautiful, because it relates directly to some lower level math stuff. You're like, how can that be showing up here? This is Calc 3, but it's awesome. It kicks ass. How would I add these two vectors? So another way to look at vectors, not just as forces, but also as like telling somebody how to get somewhere, right? So when I first introduce, this feels very much like polar coordinates, right? Because what are polar coordinates based on? What's the two pieces of a polar coordinate? Radius and angle. I love it. And how do they relate to telling somebody how to get somewhere?
Turn this far, go this far.
I love it. The angle tells you where to turn. So first I'm going to start off at 0 degrees, turn to negative 20 degrees, and then go out 7 feet, and then dig, and that's always trip, right? I want to see that pirate, the calculus pirate. All right. So if I told somebody to go this far and then go this, what's kind of wrong in the way that it's drawn? It's drawn in the way that relates to its name, but we understand. I can pick that damn thing up and move it.
Because it doesn't clarify which one I'm supposed to do first.
That, hopefully, you understand, won't matter.
But like if you were telling somebody to go there and then down, like, can you move the V to where U ends?
Totally. So I was kind of pushing us in one direction, and then I was going to say, would it matter which way I did it, actually? So, yeah, okay. So I could just redraw this here. So once I get there, then I want to go in the direction of V. So now I want to know, my picture, my scale, and all that shit could be very off. So, oh well, too bad for all of us. But now I want to know, well, where am I here? What's the result then? If I could fly, what would I do? I would just go here. So the result would be this vector. Oh, look at that with 3 colors. That's insane. So if I wanted to add U plus V, no, Jeff, there it is. That would be the result, U plus V right there. This would be the result. And if you want to kind of complete this picture, you can realize there's sort of a parallelogram thing going on there, right?
And that one is
So that blue one would be the result, the u plus v. Let me just stop there. Let that be nice. Get beyond my horrible drawing. In fact, I don't know why I'm still drawing, because I have this cool little applet thing. You guys are the best seats in the house.
Can you explain the slope of the line thing again?
Later in this semester, maybe a little bit later today too. Let me build up to it. I kind of jumped a few things because I got excited because there was a question about something I love. So I do that sometimes.
And we established that vectors always start at the origin.
All right, I want to make this really clear. I'm sorry.
Okay.
The name of the vector is this name here. This name is derived from where it would the point it points to if you did have it start at the origin.
Got it.
Where must the vector start? That's a silly question. It can start where the hell it wants to. But what's its name is the point it would point to if it did start at the origin.
Okay.
All right, how are we doing there?
That makes sense.
It's more flexible than we're used to, but it's because I want this to be a very useful way of imagining mathematics, right? What's weird when you get further and further in mathematics, you start to look back and go, oh, all that shit I did was just one way of doing things. You've already seen this. You've already seen polar coordinates. You've seen, remind me now, have you seen spherical coordinates yet? Cylindrical coordinates? All right, we're going to do that this semester. Yeah. If you're dealing with a bunch of spheres, I would rather use spherical coordinates. That should make all the calculations easier. But that's as you get further along, you're like, oh, there's a whole other way to do everything I've done before. But I'm just going to pick the way that makes the most sense for my current problem.
Just to clarify, the vector that you showed between you and me, they can start anywhere. They don't have to start at the origin point, right? You can start
Exactly. Very often when you just draw them, when you're talking about them, you will start them at the origin just so their name kind of makes the most immediate sense. But they are completely movable.
You can play quadrant 4, quadrant 3, quadrant anywhere, basically.
So just to really make that point clear from earlier, I could have picked you up and put it here, and I would have ended at the same spot. So what we just proven is that vector addition seems to be, what's the word of that property? U plus v equals v plus u. Commutative. I like it. And the further you get along in math, the more you realize that those words become very important. Algebra, the poor Math 90 students, those words don't mean shit. They just mean you can add numbers any order you want to. Yeah, but when you get further in mathematics, like matrix multiplication, is that commutative? Who knows? Is b times a necessarily equal to a times b for matrices? Sometimes you can do it one way and not the other way because the inner numbers don't match. Holy shit. So there's one example where those words start to become more and more important, right? Yes?
So, how we use vectors, we basically use them as numbers, but with multiple parts to them, right? Because especially like in that's an equation of a line right there. You put in a t, and you get a point on the line.
Exactly. I love it. So we start
you get an output that's more than one variable in it.
Say it one more time.
You have an x and y in your output. You don't put in an x, get out of y. You put in a t, you get out.
Oh, I see. Yes, I love it. So one way to look at it is I've got in one fell swoop, I've got both variables kind of showing up at once. Okay, I see what you're saying. Sort of. Is that what you meant? There's like both in there, in your face. Yes. Okay. I understand.
You didn't do that before.
Not
Except
really.
kind of with parametric.
Sort of. Yeah. All right. So I mean, this is the real basics here. You can see my vector is not starting at the origin. Right? Can I move? Yeah, I can move it around. Look at that shit. Sorry. But when I talk about the direction, very often I can use it. Now watch this. Do you see what? We haven't even talked about this. What this is, and one reason I want to show you before we even talk about this is can somebody tease out what this might mean? Magnitude. I love it. So in the book, they're going to use bold letters for vectors. Anytime I'm writing a vector on the board, it's very difficult for me to show bold. Right? It's very difficult for me to write. So I'm going to use a little sign for a vector. This applet, for some reason, doesn't even do that, but hopefully you understand that little a is a vector. And this is the length of that vector. Now, do you see, for example, look at what they say a is. Is that the point that it points to currently? I really want to bring this home.
No.
If you put the tail at the origin, does it look like maybe it's pointing to 3.72, 0.66?
Yes.
All right, good. What the hell does that mean? The blue thing is not at the origin, but it's still identified by the point it would be pointing to if it was at the origin. Does everybody, I love that. Some of you guys are like, what the hell is going on? All right, don't let that be a big deal. Just because I moved the vector shouldn't change its name, right? I'm Jeff, now I'm Bob. No, right? Now I'm somebody else. Let me talk to Sarah. She's not here. Is he taking his meds? So how do you think I can get this? We said this is the length. Of course, how would I get this length for that vector? Distance formula, 11, right? And then I don't care how many dimensions my vector lives in, the distance formula is always just as easy. I just keep adding more and more terms for the coordinates. Is everybody with me? So 3 dimensions, same idea, right? I like it. I like it. Now watch this. What will happen if I pick this up and move it towards its own tail? The vector, of course, gets smaller. What's happening to that green line? Exactly, because the green line should show only direction. So how long is that green line? 1. Okay, now, is everybody kind of with me? All right. I'm sort of teaching, and it's a stream of consciousness teaching at the moment, right? You got to excuse me. The whole semester won't be like that, but at the beginning of this course, there's a lot of little groundwork to lay with vectors. And it's just, and they all connect. And I can do this, or just move them all around. So just go with me for a little while. Okay. Let me see, what do I got right now? Let's make it something, it doesn't really matter, Jeff. This will work fine. Weehaw! Sure.